Hello viewers, welcome to my YouTube channel. In today's video, we are solving this integral. So we have integral from 0 to infinity e with the power of negative floor function of x dx. Alright, so let me quickly define the floor function. The floor function of x, so is the greatest integer, okay, less than or equal to x, okay? So that is n less than or equal to x less than n plus 1. Okay, so if that's the definition of the floor function, is the greatest integer less than or equal to x. You can see n is less than or equal to x or less than n plus 1. Are we together? Now, so if you want to solve this integral right here, so we are going to have integral from 0 to infinity of e raised to the power of negative floor function of x dx. So this will be equal to integral from 0 to 1 plus integral from 1 to 2 plus integral from 2 to 3 plus integral from 3 to 4 plus dot 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 dot. Okay, so plus integral n to n plus 1 according to this definition. All together, so we are applying this definition right here, and then we are going to let this floor function of x to be a constant when we are integrating. Okay, so we can turn it to what? Turn it to n, since we are using n to n plus 1. So we can turn that floor function to be n all together, and then this integral is in series form, so we can generalize it using summation. So we have sum of n from 0 to infinity, then of integral n to n plus 1, then of e raised to the power of. So instead of writing floor function of x here, so we write n, okay, dx. So what do we notice? E raised to the power of negative n right here is a constant since it's not having x, so we can bring it out. So we bring it out, we are going to have the following. So you are going to have sum of n from 0 to infinity of e raised to the power of minus n to n plus 1 dx. All right, so if you integrate your dx, don't forget what you're going to get is just x. Okay, so we are going to have sum of n from 0 to infinity e raised to the power of minus n, then we have x, then you apply the limit is n to n plus 1. Okay, so this will be equal to sum of n from 0 to infinity e raised to the power of minus n, then into bracket n plus 1 minus n. So n minus n will give us 0, so what you have now is 1. So we are going to have sum of n from 0 to infinity e raised to the power of minus n. All right, so what we are going to do now is to solve that series. You can see that this is a geometric series. So we have sum of n from 0 to infinity of 1 over e raised to the power of n. That is what we have now. So let's solve that geometric series, e raised to the power of minus n. That's why I just did. It's still 1 over e raised to the power of n. Don't forget your law of indices. So how do we solve this geometric series? Okay, you can decide to put the values of n from 0. Okay, so if you do that, when n is 0, you are going to have 1, plus when n is 1, you are going to have 1 over e, plus when n is 2, you are going to have 1 over e raised to the power of 2, plus when n is 3, you are going to have 1 over e raised to the power of 3, plus dot 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 dot. You understand? So the first term, which is a, is equal to 1. So what will be the common ratio? So the common ratio will be the second term divided by the first term, or it said the third term divided by the second term. Okay, so if we do that, so we have a common ratio which is 1 over e, and then we can see that 1 over e is less than 1, so we can apply the formula for calculating sum of a geometric series. So we know that sum of geometric series is equal to a over 1 minus r. This is when r is less than 1. Okay, so a is 1, then over 1 minus the common ratio, which is 1 over e. Okay, so this is the 1 divided by, so the LCM in the denominator right here is e, so we have e minus 1. So we have 1 multiplied by e over e minus 1, so which is equal to e over e minus 1. So that is a beautiful answer to that particular problem. So if you like this kind of video, please don't forget to subscribe, like, comment, and share. Thanks for watching. See you next time.